Alrighty, in this video we are going to be talking about Euler's method. Before we talk about Euler's method, as a disclaimer, this lesson is going to be very fraction heavy and algebra heavy. This will probably be on the calculator inactive part of the FRQ/exam. So it's very, very, very important that you are comfortable dealing with, let's say, fractions, because if you're not, then you're kind of screwed. That's all I'm saying. Euler's method is a numerical approach to approximate the particular solution of the differential equation y prime is equal to capital F x comma y that passes through the point x sub 0, y sub 0. Essentially, what we are doing here is just approximating tangent lines. And then once we do that, we're going to approximate the tangent line even more and even more and even more using substeps. So think about this in terms of, let's say, using the trapezoid rule, but instead of area, we're talking about approximations. So on number 1, I already gave you a table that we're going to fill out together. But then on number 2, number 3, you'll notice that I don't give you a table and you actually have to do the table on your own. But essentially, this is what your table should look like. You have x on the first column, y on your second column, your derivative, aka the slope, and then the equation of the tangent line. Remember that your equation of the tangent line is point slope. So you're given dy dx is equal to x minus y with the initial condition of y sub 0 is equal to 1. And we're going to use Euler's method with 4 equal subsizes to approximate y sub 2 using the table below. So notice how if I'm going to have 4 subsizes and I'm going to approximate 2 right here, well, and I start at 0, 2 minus 0 divided by 4 means that I have a subsize of 1/2. So notice how here I have a subsize of 1/2, 1/2, and 1/2. All right. So we are already given that y sub 0 is equal to 1. So I know that x is 0 and then y is 1. What we're going to do is find the derivative based off of my differential equation. So x minus y, aka 0 minus 1 or negative 1. Once we do that, I have the point 0, 1, and then I have a slope of negative 1. So guess what? I could write the equation of a tangent line. So I have y minus 1 is equal to negative 1, x minus 0. Now, we're going to use that tangent line to approximate when x is 1/2, because remember, my subsize was 1/2. So now what I'm going to do is plug in 1/2 into x and figure out what my y value is. Like I said, this is pretty algebra heavy. So notice how here I have negative 1 times 1/2, which is just negative 1/2. And then if I were to add 1 to the other side, this means that my approximation is 1/2. There we go. So y is 1/2 using my approximation. Now, using this approximation of 1/2, I'm going to find the derivative with my differential equation. 1/2 minus 1/2 is 0, so this means that my slope is 0. You're going to find the equation of the tangent line using your point of 1/2, 1/2, and your slope of 0. So this means I have y minus 1/2 is equal to 0, x minus 1/2. Now, I'm going to plug in 1 into my equation right here. It doesn't really matter, though, because your slope is 0, because then that's going to be 0 times whatever. So this is just going to be 0, meaning that your y value is going to be, once again, 1/2. But I'm going to write it for you guys so that you can understand where I'm getting that 1/2 from. Because this becomes 1. 1 minus 1/2 becomes 1/2. 1/2 times 0 is 0. Add the 1/2, and that's how I get 1/2. All right, now I have a point of 1 and 1/2. I'm going to find the slope using my differential equation. So 1 minus 1/2 is, plot twist, 1/2. So then, once again, I'm going to have to find my equation of the tangent line. Y minus 1/2 is equal to 1/2 x minus 1. All right, so your x value is now 3/2. So I'm going to substitute in 3/2 into my equation right here. Oops. And you'll notice something very interesting as you do this. Notice how this is 1/2. Notice how this was also 1/2. And guess what? This right here is also 1/2. So now you have y minus 1/2 is equal to 1/2 times 1/2. So now you have y is equal to 1/4 plus 1/2. And once again, this is where you need to figure out your fraction skills. I know some of you guys are scared of fractions, but you might need to suck it up. 1/4 plus 1/2 is going to be 3/4. So you know that your y value here is 3/4. Now, we are approximating y sub 2, y of 2. So this is going to be my last slope, my last equation, and then I'm going to plug in 2, and then I'm going to call it a day. All right, so 3/2 minus 3/4. This right here is the same thing as 6/4. So 6/4 minus 3/4 is 3/4. So this is going to give me y minus 3/4 is equal to 3/4 x minus 3/2. We are approximating 2, so I'm going to plug in 2 here. And once again, you'll realize that 2 minus 3/2 is 1/2. So now you have y minus 3/4 is equal to 3/4 times 1/2. And honestly, if you want to keep it like this, where you have y is equal to 3/4 times 1/2 plus 3/4, heck, that's fine with me. I don't care. But if you were to make it pretty, this is 3/8 plus 3/4. 3/4 is the same thing as 6/8. So this tells me that y of 2 is approximately 9/8. Now, we don't know what the true value of this is, but we are just approximating, saying that this is about 9/8, given that we used Euler's method. Obviously, what we can do is use separation of variables and then find out what y is. However, in this case, we really can't use separation of variables because if I were to add y right here, I'm going to have y plus dy dx, and that's not a valid way to separate variables. That's why we had to use Euler's method here. And you'll see with example 2 and example 3 that we can't really use separation of variables. So I don't know why I said that. Oops. Okay. Number 2. We have the differential equation dy dx is equal to y over 3, x minus 2. Let y is equal to f of x be the particular solution to the differential equation with f of 0 is equal to 2. And then we're going to use Euler's method starting at x is equal to 0 with 2 steps to approximate f of -1. All right. So we're starting at 0 and we want 2 steps to approximate f of -1. So I have 0 minus 1 over 2, meaning that my approximations are going to be -1/2. I'm going to create my table where I have x, I have y, I have dy dx, and then I have the equation of the tangent line. I don't know if I'm going to have enough room, but we'll pray and see if I do. All right. So I know that my initial condition gave me 0 and 2. And I want to figure out what dy dx is based off of this right here. So what I'm going to do is plug in 0 for x and 2 for y. And then I'm going to have to simplify that to get my slope. So unfortunately, you do have to simplify to get your slope to make it pretty in terms of these types of problems. 2/3 times 0 minus 2 is -4/3. So that is my slope. The equation of the tangent line is y minus 2 is equal to -4/3 x minus 0. All right. What I'm going to do now is plug in -1/2 into my equation. And then I'm going to have to simplify this because I need to figure out what y is. So here I'm going to have y minus 2 is equal to 4, 6. And then I'm going to simplify that to be 2/3. I'm going to add 2. And if I'm adding 2, that's the same thing as adding 6/3. So 6/3. Y is 8/3. So this is approximately 8/3. Like I said, this obviously is not going to be fun in terms of algebra. All right, so you need to figure out what dy dx is using that you have 8/3 as y and -1/2 as x. I know this is going to be a lot of fun. So you have 8/3 over 3, so this is like 8/9. Then you have -1/2 minus 2, which is like, let's see, that's 4 over 2, so it's -5 over 2. And then if I were to simplify that, that's 4, so -20 over 9. Yeah. Pretty nasty, I know. All right, and then you get your equation. But lucky for you, once you get to this point right here, the last step is just plugging in -1 because that's what we're approximating. So now we can plug in -1. Of course, I do want you to simplify this a little bit and actually solve for y. Don't leave it like this. You want to make sure that it's like y equals, because you're approximating -1. So you're going to have -20 over 9, then -1 plus 1/2 is -1/2, and then plus 8/3. Am I going to simplify that? No, but you can if you really want to. I'm not going to do number 3 because honestly it's the same thing. And honestly, they're all the same thing. So I'm just going to skip to number 5, where it's just a little application of Euler's method. Number 5, we have y is equal to f of x be the solution to the differential equation dy dx is equal to 2x minus y such that f of 0 is equal to 2. And part A says that the function f has a critical point at x is equal to ln of 2, and we want to figure out what the y value, y coordinate of this critical point is. Now, remember that if we have a critical point, this means that my derivative is 0. So this means that dy dx is 0, and I have my x value being 2, not 2, ln of 2. So I'm going to substitute an ln of 2 into my differential equation. I'm going to solve for y. So guess what? Your y coordinate is 2 ln of 2. If you want to make it prettier, that's ln of 4. Okay, part B, we want to find the second derivative in terms of x and y, and then we're going to use the second derivative to determine whether or not the critical point in part A is a minimum, a maximum, or neither. So The second derivative is 2 minus dy dx. And we know that dy dx is this lovely thing right here. Now, over the course of the last unit, whenever we did differential equations, I've seen a lot of people just keep it like this. However, notice how it says in terms of x and y. So you will not get credit if you just leave it like this. You want to make sure that you change dy dx into 2x minus y so that everything is in terms of x and y, or else you will not get your credit. Minus 2x plus y. I already distributed the negative, so that's why it's negative 2x plus y. All right, so we're going to use this to determine whether or not the critical point in part A is a relative min, max, or neither, and we want to justify our answer. So what I'm going to do is use the second derivative test by plugging in, let's say, our critical point of ln of 2 and 2 ln of 2 to see if it's negative or positive. And that's going to tell us if it concaves up or concaves down, which then will tell us if it's a maximum or a minimum. All right, so this is going to give me 2 minus 2 ln of 2 plus 2 ln of 2. Notice how this will cancel out, so I'm just left with 2. All right, because 2 is greater than 0, this means that our function is concave up by the second derivative test. Which means our critical point of ln of 2 to ln of 2 is a relative minimum, since it concaves up. So we know that our critical point here is a relative minimum. All right, so part C, we want to use Euler's method with two steps of equal size to approximate f of negative 0.4. Is this approximation an underestimate or an overestimate? And we want to explain our reasoning. So we know from the initial sum, it told us that f of 0 is equal to 2. If I were to use my dy dx right here, so 2x minus y, I'm going to have it right here so I don't have to go back and forth. 2 times 0 is 0, and then minus 2 is negative 2, which means my slope is negative 2. Meaning that my equation is y minus 2 is equal to negative 2x minus 0. Now, if I'm using two steps of equal sizes and I'm starting at 0, this means that my next step is going to be negative 0.2. Okay, so I'm going to substitute in negative 0.2 into the equation. That's going to give me why am I blanking out? 0.4, oh my gosh. 0.4 and then plus 2. So that's going to give me 2.4. Oops. All right. I am going to have dy dx right here. X is negative 0.2. And then y is 2.4. This is negative 0.4 minus 2.4, which means that my slope is negative 2.8. Y minus 2.4 is equal to negative 2.8, x plus 0.2. And now I can approximate negative 0.4. So now I have y is equal to 2.4 is equal to negative 2.8. That's going to be negative 0.4 plus 0.2, which eventually turns into negative 0.2. And then I am going to multiply that. 2.8 times 0.2 gives us 0.56. Oops. And then I'm going to add that to 2.4, which is going to give us 2.96. All right, so now we want to figure out if this is an underestimate or an overestimate, and we want to explain my reasoning. Well, based off of part B, we already said that my function concaves up. Since my function concaves up, this means that my equation of the tangent line approximation is going to be an underestimate because my tangent line is going to fall below the graph. So we know that 2.96 is an underestimate. And how do we know this? Because since the tangent line is below the graph of f of x, we know this because f of x is concaves, f of x concaves up. Concaves up. So that's why we know that this is an underestimate. All right, last one. This is an FRQ from 2010. So we're going to do this one, and then we are going to stop here for Euler's method. All right, so before you watch this, go ahead and pause. Take 15 minutes out of your time. Time it as you would with an practice FRQ, and then return after 15 minutes or once you're done. All right, part A says use Euler's method starting at x is equal to 1 with two subs of equal size to approximate f of 0. Show the work that leads to your answer. So we know that f of 1 is equal to 0. 1 minus 0 is 1, so my slope is 1. My equation is y minus 0 is equal to 1, x minus 1. Since I am approximating f of 0 and we're starting at 1, this tells me that I have 0.5 right here, or 1/2. All right, and then I have 1 minus y. To figure out what that is, I'm going to have 1/2 right here, which means that I have negative 1/2 as my y value. 1 minus negative 1/2 is going to give us 3/2 as my slope. And then we can approximate what f of 0 is. So in this case, my equation is going to be y plus 1/2 is equal to 3/2 x minus 1/2. And then I have 0, so I have y plus 1/2 is equal to 3/2 negative 1/2, and then solve for y. So y is equal to negative 3/4 minus 1/2. Make it pretty or not, I don't care. This is going to give you negative 5/4. 1 point will be given for using Euler's method. And then 1 point will be given for your answer of -5/4. All right, part B, we want to find the limit of x as x approaches 1 of f of x over x cubed minus 1, and we want to show the word that leads to our answer. All right, now remember that this is L'Hopital's rule. Now, how do I know? Well, if I were to plug in f of x, that's going to give me 0, and if I were to plug in 1, that's going to give me 0. Now, remember, with L'Hopital's rule, you need to show that the numerator and the denominator approaches 0 separately. If you do not, then you will not get credit. Once you do that, so you could say that this is in the indeterminate form of 0 over 0, and then you can use L'Hopital's rule. And then we can take the derivative of the numerator and the denominator. So now I have the limit as x approaches 1 of f prime of x over 3x squared. Well, as we approach 1, we know that that's going to be 1 right here, since if x is 0, then y is 0. If that's the case, then dy dx is 1. And then if I were to plug in 1 here, I'm going to have 1 squared, which is 1. 3 times 1 is 3. So you're going to get 1/3. 1 point will be given for L'Hopital's rule and correctly doing it. And then another point will be for your answer of 1/3. All right, C says find y is equal to f of x, a particular solution to the differential equation with the condition of f of 1 is equal to 0. So here we are going to be using separation of variables with dy dx is equal to 1 minus y. We have 1 over 1 minus y dy is equal to dx. Integrate both sides. Now, this is important because if you are going to use u substitution, make sure that you actually use u substitution. And notice how here your y is negative because you have a minus y. Since you have your minus y, this means that your du is going to be negative. So make sure that you have a negative right here because over the last couple of FRQs I've seen, you guys keep on forgetting about this negative. Okay, we have the initial condition of f of 1 is equal to 0. So I don't care where you substitute n1 and 0. If you want to do it now, you can. If you want to do it later, you could do it later. I'm just going to do it now. Okay, ln of 1 is 0. So you have 0 is equal to 1 plus c. So c is equal to -1. So now you have negative, the absolute value of 1 minus y is equal to x minus 1. I'm going to multiply by the negative. So then I have 1 minus x, or negative x plus 1. I'm going to take the e of both sides. So I have 1 minus y is equal to e to the 1 minus x. I'm going to add y and then subtract the e to the 1 minus x, or, solve for y, however you want to do it. So you have 1 minus e to the 1 minus x is equal to y as your answer. All right, so we're going to get points. Your first one is going to be using separation of variables. So that's 1. You're going to have 1 point for taking the antiderivatives of both of them. You're going to earn 1 point for you having a plus c. You're going to have 1 point for solving for c. And then you're going to have 1 point for solving for y. And that's going to be 5 points for part C, 2 for B, and then 2 for A, which gives you 9 total points. And hopefully you got those 9, because this was kind of low-key and easy FRQ to do. All right, in the next video, we will talk about logistic models.